Dobrý den and hello. I'm Peter Michalek, and similar as Georgia, I come from the CDT, Center for Doctoral Training in Cloud Computing for Big Data at Newcastle University. The difference between me and Georgia is Georgia has still plenty of time to explore and have fun at the PhD because she's in year 2. I'm at the final stage, at the write-up stage. So thank you very much for the invite, because this is a great opportunity for me to take a break from such an exciting task of writing. This is my team, without which I wouldn't be able to do anything. My main computer science supervisor is Paul Watson. Any problems with the statistics, I deal with my second supervisor, Sarah Heaps. And one of the use cases is coming from the medical school from my third supervisor, Mike Trenell. So I introduced the data streaming tasks, or what devices we are using, and then I'll explain a little bit about the challenges of automating the placement of computation in the IoT environments. And I'll explain our perspective and the angle which we took. And the clicker is not clicking. Oh. So, as you know, there is a variety of IoT devices, and the market is just booming with the new devices, and some devices are disappearing from the market. Because of the healthcare use case, we focus on the healthcare devices which produce data about the well-being, such as activity trackers, so smart watches, or advanced sleep trackers, such as Oura Ring, but also something more advanced and more medical as continuous glucose monitors. So Dexcom G6 is a small semi-implantable device which is used for diabetes patients to help them manage their conditions better. So this device is put into your belly, and it can stream the data over the Bluetooth device directly to the phone with the accurate measurements of the glucose every 5 minutes. So as I said, this data usually has to hit a field gateway, such as a mobile phone or a Raspberry Pi, because the devices do not usually have direct connection to the internet. And in your normal stream processing task, you have to go through some message broker, and then when you hit the cloud, and actually the questions which you are posing is answered through the stream processing engine, so all the data usually is streamed directly to the clouds to answer the question and get the insights out. The PhD which I'm working on and been working on for the last 4 years is all focused on, can we analyze automatically which parts of the computation usually happen in the clouds and push them automatically on the devices. But you know that there are some challenges. So if you are designing a task for the IoT streaming use case, you hit the problem of the battery life, but also there is a problem of the bandwidth. So if you are on Wi-Fi, all is well, but what if you are on cellular? So there is a premium which you have to pay to transmit the data, or you use a different form of network, as we touch on later on. Also, if your application gets popular and there are thousands of users using it and start pushing all the data to the clouds to get the insights, you get a high load there, and you will need more virtual resources. So as I said, analyzing which part of the computation could be automatically pushed as close to the devices as possible is the research questions which we are trying to tackle in my PhD. And also we need some feedback loop. I might stand just here. So just give you a flavor about the use case which I'm working on. On this figure, we can see glucose data, which is the black line in the middle. These are the healthy boundaries for a typical person, and superimposed is the activity summaries on the bottom. As the time goes and we get the data, we can evaluate it, and such as in this case, there is no need to take action because all looks good, so all is well. However, this is not the case, especially with the diabetes patients. So if the statistical model evaluates that there is a high probability that the person will go into hyperglycemic episode, this is a perfect time for us to issue a behavioral prompt. And actually, after the snack, all of us are probably heading this way right now. So the behavioral prompt could be a text message on your mobile phone, or a notification on the wearable device asking the user to heighten their activity in order to attenuate the upward glucose trajectory, so to bring the glucose levels down. Also, similarly, very important is educational aspect. So the clicker is that. We can provide feedback after the patient recovers from the hyperglycemic episode, because we know whether they took an action and went for a walk, or we can let them know that also their inaction has a dramatic effect on their well-being. And the motivation for these patients to stay as close as possible within the healthy boundaries is tremendous. So just to outline the challenges which we are facing, just given the couple of devices which are used in this use case, you can see that the variety of languages the software development group would have to use is quite vast and is increasing with every device added. But also, there might be some non-functional requirements placed upon the system, such as energy or performance or the bandwidth restrictions, which the team would have to deal with manually as well. So there are two possible solutions. One, as I described, yes, give this task to a software development team and let them design a bespoke solution for this problem. However, as the title of my talk suggests, we went down the route of automation. So can you imagine a system where you design your queries and you send them to the system with a non-functional requirements, and the system automatically distributes the computation across your infrastructure without you needing to know C or JavaScript or where the computation actually will happen? So this is the tool we've been working on. It's called Path2IoT. And it has a couple of components. Of course, as I said, it requires input, and we went with a high-level declarative language, which I'll give you a flavor in a minute. Resource catalog just provides the information about current state of infrastructure and its capabilities. And also, there is an interface to supply your non-functional requirements for the task ahead. The core of the system and of the PhD is the PATHfinder component, which has several stages, and I briefly outline what happens at each of them. But basically, it decomposes the queries and explores the space of possible deployment plans and narrows it down using the cost models to pick the winner. Then following is the PATHdeployer tool, which actually enacts the computation and supplies the configuration to each of the components in order to answer the questions we are posing. As a future work, and because of the volatility of the IoT, monitoring system would be needed, which could trigger a dynamic re-optimization if the infrastructure changes, such as if the battery level drops or some network components get congested. As I mentioned, we use high-level declarative language, and we went with event processing language, EPL, which was defined by ESPA, which is Complex Event Processing Library, and it's open sourced. This language is extension of the SQL, so it's SQL compliant. However, it allows you to express the temporal dependencies between the streams and events, and also it gives you an ability to deal with the unbounded streams, so you can use different types of windows in your queries. So actually, a lot of developers are familiar with the querying traditional SQL, and this is just one step they need to take to be able to actually process the real-time data streams. To give you a flavor, so these are the 5 queries which actually take the raw accelerometer data and turn them into activity summaries. And in this case, this is the simple step count algorithm. You can ignore the query 1 and 5 because these are just user-defined functions to enact the data sampling and to actually persist the data, the final output in the database. With the query 2, many of you might be familiar. It's just the transformation, is a calculation of Euclidean distance and some filtering. With the query 3, you can already see match recognize, which is a clause which was added to the EPL language to allow you to define what dependencies there might be on the events. And this query is only triggered if all of this pattern which you designed is satisfied. And then we have the query 4, which just aggregates everything in the 2 minutes window. The beauty of this is that the tool takes the queries such as this and turns them into directed acyclic graph. So this is the internal representation of each of the operations as defined by the queries, joined up together by the Optimiser, and it creates a digital image of these queries using Neo4j, so we quite rely on Neo4j to traverse the trees. Again, due to the time, the next phase is that once we have the plan, the logical optimization is the first step. So there is a series of optimization techniques which we can apply, but the most useful what we found is operator reordering. So actually you can reorder the logical plan and create the copies of it in order to explore what are the possibilities of deploying the queries, perhaps in different order, but you can also discard some unnecessary projects and even reorder selects of windows. In the second phase is the physical optimization technique, where we take all the logical plans and now we look at the infrastructure and we are starting to map the operators directly on the devices which we have. And this is done also automatically. And you can see there are 225 physical plans just coming up from these 5 queries. So very important part is the physical plan pruning, where we remove the plans which are not possible to be deployed. For example, due to Optimiser places a persist to database operator on the wearable device. This is not possible, so this plan will be discarded. We still arrive at the 18 physical plans which are deployable. However, we need a way how to pick a winner. This is where the cost models comes in. So for this use case, we are exploring the energy model, which we design by this formula. It consists of 2 main components. The first component is the cost of placing an operator on the infrastructure, and also actually the wearable device, of course, is using part of energy, even if it's not doing anything, just the operator system is draining the energy. However, the bigger part of the energy impact is due to wireless data transmission over the Bluetooth. So we designed this part of the formula ensures that depending on the number of messages, we can express how much energy will be used per plan. And if you ask, how do we derive these costs for individual operators? Well, I took apart a couple of Pebble watches. Some of them didn't survive the surgery. So what I did, I just opened it up and I removed the battery, and I used the Monsoon power monitor, which is a benchtop device, industry grade, which gives you a really nice readings about the power consumption with the granularity of 5,000 hertz. So you can really see when the device is draining energy. And just really quickly to give you an overview, this is a 120-second cycle on the Pebble watch. The first phase is when the watch is trying to establish the connection. So it's just right there. It's trying to establish the connection with the mobile phone. The second phase, you can see the energy consumption is quite high. This is where the data transmission actually happens. And the third phase was something unexpected, because I could not kill the Bluetooth module programmatically and see. Actually, every time you establish the connection, there is a waiting period that the watch is still expecting maybe some messages coming from a mobile phone. So this is some cost we need to include in the formula as well. But if you look at the biggest part, the number 4, this is actually the drain just caused by the data sampling and the pre-processing on the watch. So it's much lower. So coming back to the formula, these are the operators we measured. You can see that there are point estimates in millijoules. However, I have to stress that expressing uncertainty is so crucial, because you can see that there was a lot of variety within the power measurements. So this is something what we've done in 2 different ways. So 95% confidence intervals, just a simple way. But more robust way was when we used Bayesian regression model, but we will not cover this right now. So this cost model helps us to look at these 18 plans and pick the one which is consuming the least amount of energy, but still satisfying the questions we are posing. And the next step is actually, how do we deploy this? So the PATHfinder tool decides which plan to pick. It sends it to a PATHdeployer, which uses 2 phases to deploy based on the industry-proven technologies. We use Zookeeper for configuration management. D2Esper is our in-house build. It's just a dynamic wrapper around the Esper that allows us to send queries dynamically. So we can just spin these Docker containers, and they just sit there connected to Zookeeper waiting for the commands. And then ActiveMQ just for message passing, and InfluxDB for just as a database for the final outcome. However, with the IoT deployment, it's not so straightforward because you cannot really connect a wearable watch to Zookeeper. So we went different path. Pre-installed IoT engines are pulling for the configuration changes directly through the REST API. Once the deployment system pushes the configuration for each component inside the database, they pull regularly. Once they get it, they start computation. Just briefly to describe the results and just to focus on the two important ones. If we would execute all of the processing in the cloud and stream all of the data immediately as it becomes available, we would consume quite a lot of energy. However, the optimized, the best plan, uses significantly less amount of energy. And just in numbers, the battery life improvement is quite dramatic. So we would drain the battery within 18 hours on the baseline plan. The normal battery life of a Pebble watch is 7 days, around 7 days. If it doesn't do anything, just shows time. The optimized plan extends this to around 80 hours, and given the confidence intervals. So because I didn't cover the logical and physical optimization steps, just to let you know what happened, on the left we can see the original plan as it was decomposed from the queries we posed. The optimizer actually decided to push the window operator a bit closer to the source of data, and then the placement happened. These operations happen on the wearable and these in the cloud. The mobile phone just transmitted the messages. There was no focus on offloading on the mobile phone at that stage. Due to the time, I'll just cover second use case very, very quickly, just to let you know that this tool was not really built as a bespoke solution and it can handle a variety of use cases. The working title is Train Busters because I'm catching metro trains. So this is a metro train running around Newcastle. So we've got a nice network in Newcastle of 59 stations. The annoying part, this is a very selfish use case because I was always annoyed when I just read on a Twitter, the metro is delayed, apologies. But I didn't know when to run. So I started with my station, Monkseaton. I wanted to know where are the trains. There are many ways how you can detect the train arrival. However, I went with the audio signal. So Georgia explained very nicely how to process raw audio signal using digital signal processing techniques and filtering and Fourier transform and picking dominant frequencies. So I will skip all of that. I just want you to see that this is a train arrival on the platform. So there is some humming, some announcements, but the signal which needs to happen every single time when the train is there, this is for the door opening. And this is door closing. And that hit me. If I just focus on these two noises, I know that there was a boarding going on. What I did, as Georgia explained, yes, clearing up the noise and all of that, I was more interested what are the limitations of expressing this in event processing language, and this is it. I will not go through it, but you can see these are a bit more complicated queries, which are threshold-based detection of these two signals. So door opening has to happen, door closing has to happen within certain intervals. If both of these conditions are satisfied within given time, say that the train arrived and send it to the just to a message broker to notify whatever consumer is interested. Again, just to give you an idea what this looks like inside of Optimiser, this is the directed acyclic graph the Optimiser has to deal with. So again, it's a little more complicated. It's 32 operators. But I didn't tell you what we are optimizing for. So we wanted to explore something different. So we went with the bandwidth. On the platform, there is nothing. There is no Wi-Fi. I refuse to pay for the cellular connection. So I went with the LoRaWAN technology. So this is a gateway. It's quite impressive. It's one of 3 quite popular low-power, wide-area network technologies currently on market. It operates in unlicensed band, so there are no fees to pay. However, there is cost to pay in terms of how much data you can transmit. So this is really limited. This is highly theoretical. I never seen 20 kilometers. I heard of 10 kilometers line of sight, but in urban areas, sometimes if you go around the hill and there are buildings 600 meters and you don't get the message. But it allows the private networks. For the optimizer, yes, there is clear restriction, the payload size. The Things network applies the fair usage policy of 30 seconds, and there are some European regulations which needs to be considered as well. So this is fed in to an optimizer as a cost model, and just to wrap up, to let you know how many possibilities there are quite a lot. Even after the pruning, there's almost 15,000 of them. And just to give you a flavor of some, if we wouldn't do anything, just to send the data, which is not possible because it's 44,100 hertz sampling of the audio, you cannot send it over LoRaWAN. However, as you start to push more computation on the Raspberry Pi, you get to a reasonable amount of data you need to send and reasonable frequency. So again, this is just to prove that the tool can be extended and has been extended to cope with different objectives. So just to wrap up, because I ran out of time, what I presented today is the research on automatic placement of operators using high-level declarative language. The tool is open source. It takes in and decomposes these queries. The logical and physical optimization steps can be extended. We explored energy and bandwidth, and there is a deployment architecture in place which was tested on this use case. For the future work, as I said, there would be really a need of monitoring system and to enact the re-optimization automatically on the infrastructure change. And there is some other reading. If you would like to know more about the Optimiser itself, is the first paper. The second one is, if you are more interested about, we teamed up with a team of statisticians to look at automatically partitioning machine learning algorithms, or parts of it. And the last one is extension of the cost models. So thank you very much, and if you have any questions.
Thank you. So, do you have any questions?
Thank you. So I wonder, considering that the point of this research was to reduce the time spent on development, like bespoke development of things, you still need to, model. You still need to put together the energy models and a few other things. So how much energy, how much time do you think is saved by your solution compared to bespoke systems?
Yep, this is an excellent question, and the amount of time is 4 years. I spend on this all the time. However, yes, I agree. There is a lot of development effort needed. But once you get it set up for each of the platforms and you push the capabilities of these platforms to the maximum, then you can hand it over to someone who has no idea what is happening, such as domain expert, and they just want to prototype. They want to see what is happening. So maybe they just know how to write the SQL query, but they would be overwhelmed by all the other steps. So yes, there is a balance needed, but this approach can be flexible, more flexible.
So how do you account for the different hardware capabilities of the devices which you're targeting? So let's say the CPU in the Pebble probably doesn't have any vector computing and so on. So the efficiency rating we get for the same kind of computation on the large CPU is much higher than on that thing.
Yes. So this broadly comes to the physical optimization phase, when the tool compares the capabilities of the platform with the definition of the operator. And if there is a mismatch, and this all comes from the resource catalog, so all of the work on how much energy each operator costs, what are the capabilities of the Pebble Watch, these are all inside of the resource catalog, and also the definitions of the operators. So if the operator says, the only connection which I can use is, I don't know, LoRaWAN, and you try to place it on something which doesn't have the LoRaWAN connection, this plan will be discarded. So it's the comparison in between the definitions, really. I hope that answered your question.
Is there something in the algorithm that takes into account the connectivity? Because you presented a few examples that we might have connectivity issues, and we might need to hold information in the edge device and account for it coming back online, like the data center coming back online and everything.
So for the first part of your questions, I was keen to say, yes, 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 we do that. So what we do, there is a definition, for example, on a Pebble Watch, how much RAM it has per application, not general, how much can be used. And this is used to calculate the maximum window size. If there is a possibility to squeeze even more in the window, we could and we would. So the plans which require more RAM would not be executed, they would be pruned and discarded. However, when you say, when the network goes down and it reconnects, this we have not implemented anything, any sort of like that. So in my mind, what you're asking is give a tolerance or possibility to for the device to go offline for 2 hours. Is that? Yeah. So this is not implemented. This is not implemented. I can think of how it could be implemented because in the resource catalog, again, there are definitions of the network capabilities. So we know there is a Bluetooth connection on the Pebble Watch. We know there's Wi-Fi, cellular, and Bluetooth on the mobile phone. And there are definitions of how much the link is. And we know how much memory is here. However, the cost model at the moment it does not allow you to specify anything like this, but it could. I try to design all of these tools to be as self-contained, modularized as possible. That's why the research group, when they approach me, that they want to look at the preferences for the user, so the user can say, oh, we think that the monetary cost is not as important as latency. They find it quite easy to extend and replace the cost models inside of the Optimiser. So it's possible to extend, currently, no.
Okay. So thank you again for a wonderful talk.
Thank you.